Welcome. Thank you for humoring me and coming down beyond the ribbons on the sides. Our goal here with the Back to the Classroom was to have a little bit more intimate setting, and you'll find that the two faculty members that we have here today are going to ask for a little bit of participation, and it's a lot easier if you're down a little bit closer to the front rather than in the back to try and help out with the participation in the sessions today. I'd like to welcome you to the System Design and Management Conference. It's sponsored by the System Design and Management Program, or SDM, here at MIT. SDM is a mid-career master's degree program that's jointly offered by the Sloan School and the MIT School of Engineering. The program involves a systems thinking perspective. It integrates management, technology, and social sciences to address rapidly accelerating complexity and change in today's global markets. Graduates of our program earn a master's degree in engineering and management. Annually, SDM sponsors a conference, and we look to dig deeper into current topics on systems thinking. The aim of the conference this year is to provide practical information from multiple disciplines that'll spark ideas that leaders at all developmental stages can apply to real-world challenges. In years past, we received feedback from conference attendees asking to understand a little bit better about what we teach here at MIT. We also heard back from some of our alumni that said, we've been out for 5 years or 10 years or 15 years, and I know things have changed and evolved in what you teach, and we'd love to hear a little bit more about what's being currently offered inside the classroom. And as a result, we're pleased to offer this afternoon's Back to the Classroom session. Both of the faculty members that are here today teach in our core systems course that's the foundation of our SDM program. They're bringing to you today a sampling of the lecture material that they present in the classroom. I'm pleased to welcome Chi Hommes and Brian Mosier. Presenting first this afternoon is Dr. Chi van Eikema Hommes. Dr. Hommes is a lecturer in the Engineering Systems Division here at MIT, and she teaches system engineering in our core. Her research interests include complex system design theory and methodology, system safety, product development, and product architecture. Dr. Hommes is also a senior staff engineer at the Volpe National Transportation Systems Center. She leads their research efforts on system safety for automobile electronic control system. She holds both a Master of Science and a PhD from MIT's Mechanical Engineering, Department of Mechanical Engineering. In this interactive Back to the Classroom session, Dr. Hommes will compare and contrast systems thinking with scientific thinking. Traditional science and engineering disciplines are built upon scientific thinking, but such thinking can prove limiting in the face of challenges of modern, complex sociotechnical systems. Systems thinking is therefore needed to address these new challenges. With that, I would love to introduce Dr. Chi Hommes. Thank you.
Thank you, Joan. Welcome, everybody, to the classroom sample. So let me get the clicker. Joan has very nicely introduced my background, and I just want to make a disclaimer here today. As a government employee, I want to say here, everything I speak of and discuss here represent my professional capacity at the MIT. It does not represent any message, any direction of the US Department of Transportation. All right, so let me begin by introduce a bit more about why I'm interested in complex system design. So after I graduated from MIT with a PhD degree, I decided to go to industry. I wanted to be a good engineer and make something change the world. So I went to the automotive industry, and I was assigned to be a lead warranty problem resolution engineer in one of my assignments. And it proved to provide a lot of frustration, but inspiration as well for my research. So here's an example. In the automotive industry, there are a lot of vehicle problems we call trouble not identified. So in this case, we had a big warranty bar, cost bar, leading the whole company on one of our vehicle platforms. And basically, people are bringing the car back with the check engine light on, And when you plug in a diagnostics tool, it gives you a code that says the right bank of the engine is running rich, meaning there's too much fuel in the combustion process. And they said, okay, what's the problem? And they started changing out, the technicians started changing out the spark plugs, the fuel injectors, all the components you can imagine, and the customer kept on coming back. Eventually, after several repairs, and remember, these are within the warranty repairs, so all the repair costs go back to the company. After several of those trips, customers frustrated, the technician finally says, okay, let me swap out the computer. And that was many years ago. One pop of the computer is $400 back to the company. So imagine how many of those can, the amount of money that can stack up to. And even though the computer is swapped out, temporarily the problem is resolved because all the codes and everything is cleared out. Eventually, customers still come back and says, hey, the check engine light is on again. And the problem, many problems like this, does go away on our quality charts because vehicles go out of warranty. So they don't show up on our cost anymore. Doesn't mean we fixed the problem. Now, in this particular case, what happened was I got the problem, and I started going around to the component engineers. I first go to the easier ones, fuel injectors. I go to the calibration people, the engine folks, and ask each one of them, is there some kind of hardware issue you know of with your supplier with this particular engine or vehicle program? And everybody gave me the same answer. Hey, we share components across platforms. And nobody else had a complaint about this particular program, so it couldn't be my part. It has to be somebody else's. Why don't you go to the next person? Let me recommend so and so. It might be their part. And including the software, they say, hey, even the software, although it's complex, it is written based on the software line, product line platform approach. So this is nothing that different from other software, and why don't you go check with the calibration? Calibration says, hey, we calibrate every parameter following the same process. If you say the process is wrong, then everybody's wrong, but you're the only one came back to complain. So move on. And I went around that circle a couple of times, eventually got very frustrated. And what had dawned on me at that point is that, in fact, it's probably true that every component in this whole system were designed and are performing the way they were supposed to. They're all good components. They're all meeting their requirements. What is the problem is how this combination of components, when they're together in this particular vehicle formation, the system integration, and this particular performance space of the vehicle, the interaction among them probably isn't all that satisfying. And to study that interaction and redefine how each component needed to perform in that context is not possible once the vehicle is already in production because the company resource isn't there anymore. So the resources are shifted to the new program. So many of these cases came through my desk and had unsatisfying ending. And I was frustrated because I thought, hey, a PhD from MIT didn't help me save the world. And eventually opportunity came up, and I came back to MIT as a research scientist, and these have been motivating factors for me to keep on studying how can we design systems better, in addition to design better components. So that's a small thing. It's a quality thing. It's money lost for a certain company industry. There are much worse things that can happen when we don't think hard enough or don't know how to address system interactions. And many of these, the most severe forms I think we see are in accidents that cause injury, loss of properties. This particular one is very interesting. You can look it up. The link is there on Wikipedia. It's I think it's 2002 in Überlingen is a town south of Germany. I'm just going to go with memory. What happened was there is a mid-air collision between two airplanes. One of them is a Russian passenger airplane carrying a large amount of, I think, 60-some school children on a field trip. The other one is a DHL cargo plane. And the two planes were flying, and their altitude got very close. So this was detected by two kinds of controller. One is the ground air traffic controller in Switzerland. So the Swiss air traffic controller saw that coming on the screen. And he made a decision for one of the planes to go lower to avoid this collision. And he gave this issue, he issued this command to one of the airplanes. And the other set of controller are automated computers on the plane called automated ATCs, collision avoidance systems. So there are computers on, and the sensors on the airplane that can detect imminent collision and issue commands to the pilot automatically for them to avoid each other. So the plane that received the air traffic controller's command heard the computer telling them to go higher. The air traffic controller told them to go lower. And they followed the human controller's command. And they said, all right, the controller told me to go lower, I'm going to go lower. Now, on the other plane, the computer told them to go lower because the other computer told the other plane to go higher. So both planes went lower instead of trying to avoid each other, and they collided in midair. So in total, 71 people died, and all lives were lost. And the political implication, actually, if you read the story, it was even worse because the Russian family, there was the husband lost his children and a wife in this collision, and he believed the Swiss controller was the murderer. So after a year or two, he went to Switzerland and murdered the air traffic controller. And he went back to Russia, and he was recognized as national hero and elected official eventually. So you can read it. It's quite an interesting story. But what this tells us is, what we learned, there are two lessons. One is large, complex sociotechnical systems. In these systems, when something goes wrong, the implication is huge. It's not a few dollars lost. It can have huge societal, political implication. The second thing we learned, again in this case, is if you think about every component in this system, the air traffic controller, the pilots, the onboard collision avoidance systems, every component did exactly what they were designed to do, or they were supposed to do. Nobody did bad things. Nobody, missed their task. But it's this interaction among them, this conflict between the human controller and the computer controller, and the unfortunate combination of that was not considered in the system design. Therefore, we had this unintended consequence and unfortunate outcome of the collision. Here's a chart we flash a lot in our classes, and it summarizes what we've discussed. And as the life cycle of the system go from requirements, it goes through requirements design, development, testing, field operation. The further down the road you go, number one, the harder it is to change any of the design. More and more of the design is locked in. Number two, the cost of changing is much, much higher as you go further. So my personal motivation, I think it's the same as the way we teach the core course, is we want to prevent these late occurrence, these losses and failures late in the process as much as possible, and design the consideration in early on in the process. So my research interest is really in the earlier stage of the design process, and to try to learn from what happened, the mistakes we made, and try to bring them back as requirements that feed into the product design. Joan has touched upon that. I won't spend more time on that. So today, the lecture I have chosen to give, and I personally is one of my favorite lecture, is a more philosophical lecture. So we won't be teaching tools, methods here in the setting, but what I want to get everybody to start thinking is, what is system thinking? We keep on talking about system design management, system thinking. What really is it? And how is it different from other types of thinking? In particular, scientific thinking, that most of us, if you're an engineer, you're brought up in that environment. So I want to get us thinking about that, and as you go through the talks tomorrow, perhaps set up a framework for you to appreciate more of what we offer in this program. All right, so to get started talking about system thinking, let's talk about what are systems. Here are some dry definitions from the literature. We have quiz for students to remember these. No, we don't, but you can read it. The systems are defined in many literature in different ways, but in different sentences, written in different sentences, but they're pretty much meaning the same thing. You know, you see a lot of components. They mention interactions. In the engineered systems, we particularly also emphasize that our systems, the system we study, usually have a defined purpose. They're different from the natural system, where humans are not part of the design. So get us thinking more about system. So why are we interested in system? Here are some pictures, I think, are systems, but also I'm sure all of you have been working on large complex system, hence interested in our program and the conference. So I'd like us to have a little discussion. What kind of system have you been working on? What are some of the characteristics make them different from non-systems? Is there such thing that's ever non-system? You can talk about what you've worked on. We can look at these pictures, pick one of them, and have a discussion. Do we want to take a minute, maybe talk to the neighbor a little bit, just chat a little bit about what you work on? What makes systems challenging? This is when TA starts scoring whether you participate in the class. And when you're ready, yes, Genevieve.
My name's Genevieve Flanagan. I work at John Deere. So I'm just going to kick it off since you're looking for
Thank
some
you.
input. One thing I
Absolutely.
found interesting, so I'm a diesel engine person. Started off at Cummins out of school. And I worked with diesel engines, which are a highly complex system, especially with emissions regulations we've got coming up. They're passed now. And so I thought that was really interesting to be on that system. And one thing that I've gone through in the past couple years now is as I went through this program, I realized that the engine is not, in fact, the ultimate system as I thought for many years. And now I work on the construction vehicles that the engines go into. And then I realized, well, this is the ultimate system. And as we get more into software now, I'm realizing, well, it's in fact not the ultimate system. It's the construction work site and so forth. So that's been an interesting learning process for me to kind of step through the stages of development of a system throughout my career.
That's great. Thank you, Genevieve. You actually, this is a great example leading into some of the later discussions we'll have. So what you have described is this hierarchy of system, right? And perhaps you're answering this question, is there such a thing ever not a system? I think in today's world, even not today's world, things are always within the context it is in. So depending on the layer you're looking at, there's always a layer above you that you need to consider in your design. Thank you. Anyone else want to add or give us another example? Yes, please.
I work in quality management systems, and in particular, we have a group of subsidiaries to our company that have all come together to form a loosely knit organization. And so having everyone work to a set of standards and a quality system and agree to how they're going to do that is a challenge.
So you talked about humans, people, and as everyone who worked with complex systems, it's not just about the technical system. It's not just my sensors and actuators. It's the people that are designing them, how they interact, their thinking, and the culture you try to cultivate, and where everybody's go, how they're motivated. And in this program, that's a huge component as well. Thank you. And we'll touch upon that factor a little more today. I have brought an interesting example. All right, great. And then one more? Yep.
Hi, I'm Raj. Here.
Oh, yes.
I work on building entrepreneurship ecosystems in colleges, regions, states, primarily in developing countries. and working with dealing with cultural issues to attitude issues to funding and policy and such.
Wonderful. And what are some of the challenges you see? Give us an example.
Oh, the challenges primarily I teach entrepreneurship education in India primarily as part of my thesis and when I was studying here.
Great.
They have the technical capability. It is primarily exposure to the thinking and innovation, entrepreneurship, and basically confidence. It primarily comes down to how do you build their confidence to do certain things.
Yeah, thank you. Thank you. So again, it's a factor side on the human side. On the human side, the human is such a big player in complex systems, so we don't want to just focus on the technical, we want to focus on the socio-technical system, the leadership side. How do you make the human perform more efficiently and better? That's great. All right, so I'm sure there are even more examples. And some of the characteristics in our classroom discussions have come up are these things like interactions. We talked a lot about human interactions, component interactions. Talked about hierarchy, which Genevieve had touched upon, the hierarchical view of a system. The emergent behavior when these components interact that you can see at the lower level of the system, which we will talk a little more today about that as well. Systems are dynamic. Things change over time, and you have to be able to address that change, and it's one of the challenges as well. Interdisciplinary, when a lot of people with different backgrounds come together and try to achieve the same goal, how do you work with that in a team and be able to succeed? So these are complex systems, and what have we taught students in most of the engineering school? What we've learned, I'm an engineer, hardcore mechanical engineer. My qualifying exam is all dynamics, fluids, control system theory. So you can imagine it's all technical courses. So the training we've gotten in most of the traditional learning is scientific thinking. How do we think scientifically? And I wanted to review what that is and discuss what are the challenges the complex system poses to that kind of thinking. And then introduce the idea of system thinking and how it's different. So scientific thinking comes from the development of science. Science is a reflection of human being that always want to find the regularity around in the world around us. We don't want to be confused. We want to find the rules so we can have some control over the occurrences around us. And it's quite new. The scientific revolution, it hasn't been that many centuries, 400 years so far, but it has been one of the most powerful inventions of humankind. It really changed our lives. And before that, we had a religion. So the Cosmos recently, the new Cosmos series, it was a nice illustration of the history of science and how we come to where we are. If you're ever interested, you haven't watched that. That was a great show. So disciplines in science, in traditional science, you can see in the history, science really, the different disciplines didn't occur all at once. It was a process. It was an evolution. We first, at the beginning, had the mathematics. People were trying to use numbers to represent what happened in the world. And from mathematics evolved astronomy. Then comes physics, chemistry, biological sciences, and sociology. And in the history, every new discipline occurred because people tried to use the existing knowledge, existing discipline to explain more and more phenomena, and they found that there's limitation to that. So every new discipline emerged because there's something more complex that needs to be explained, and there are irreducible laws within that discipline. But it's always built upon the previous knowledge. So none of these scientific disciplines are separate, away from each other. And the characteristics of scientific thinking, there are three main characteristics. One is reductionism. The second, repeatability. The third, refutation. So let me expand on each one of these a little bit. Oh, I clicked the wrong button. All right, so what's reductionism? very simply explained, is divide and conquer. That's how we tackle the complexity in the world. When you have a complex problem, that's always what we do. You divide it. And you see that in every discipline. It's about simply using controlled experiments where factor settings can be controlled, and you can observe the results of the actions. And another thing like the law of parsimony, scientific reduction, all of these are just typical approaches of reductionism. So let me give some examples. Here, Aristotle famously said the world is formed by fire, earth, air, water, and ether. So what he's saying is, okay, this world is complex, a lot of things happen, but basically they can be explained by 5 elements. That's reductionist thinking. Archimedes said, how do we measure the circumference of a circle? You approximate it by smaller and smaller length of straight lines. Eventually, you can describe the circle by infinitely small straight lines. So dividing the circle into straight lines and add the length up to approximate the circumference, that is his way of dividing and conquer the problem. Another example of reductionist thinking, Cartesian coordinates, right? We describe the space by Cartesian coordinates. X, Y, Z, you can specify any point in space. So that is also, again, dividing the world into orthogonal factors. Galileo's experiments. Galileo famously has conducted many, many physical experiments. And here is one example of it. I have a link on the PBS website. If anybody is interested, there are some cartoons and explaining what kinds of experiments he's ever set up. But in this case, he was trying to find out if a ball was dropped from the same height, but rolling down an inclined plane. Depending on the changing angle of this inclined plane, would that change the final speed of the ball at the end of the plane? And how would that incline change the time it takes for the ball to reach the bottom of the plane? So what do you think? Do you think the ball at the end will have different speed depending on whether you set the end of the plane to A or B or C or D? What do you think? The final speed of the ball. Does it remain the same? Or is D faster than A? No takes on this? Guess I don't have to worry about scientific thinking. What he has proved, and in this case, again, this is a controlled experiment. The incline is not very long. The surface is probably smooth enough. The final speed is the same because you're dropping off from the same height. So the potential energy converts to the kinetic energy. The speed is the same at the end.
It's actually wrong. Right? If you measure it carefully enough, it's not. Because there is some fact.
There is some friction. It does matter. So that's another important point of scientific experiment, is you will design your experiment so that you control the factors you're measuring, right? So if you put...
Right, so if you did our friction surface in a vacuum, it would be the same. Right? Galileo did, he just didn't have very good clocks.
He didn't have that's another thing. Being able to measure is very important as well in the scientific experiment. So scientific experiment has all these things about controlling the factor, being able to describe a phenomena using a set of factors, break it down to the factors, finding the relationship among these factors, being able to control the environment the experiment is in, and being able to repeat it over and over again with the same setup so that your results is repeatable. So these are all examples of reductionist thinking. You take a complex phenomena, you break it down to factors and find the relationship among these factors. So it goes into our second characteristic is repeatability. What this gentleman just mentioned about doing it in a vacuum, maybe you put some rougher sandpaper on the incline versus a smooth plane, that'll create very different results. So you control for these factors. Once you control for these factors, this experiment and the results are repeatable. No matter who performs it, where, when, on Earth, of course, we don't want a different gravity, but it's repeatable. So everybody can come, conduct the experiment, and say, hey, yes, it's true. I got the same results. And it's always measurable so that you can compare the results. That's very much scientific experiment. And the progression of science and scientific laws, findings, is based on refutation. And that's why you see researchers argue so much with one another, because that's how you push your discipline forward. Science always progresses by refuting somebody else's discovery with more facts and more understanding. So we're more interested in refutation than corroboration in science. So these are the 3 characteristics in scientific thinking. And a perfect piece of scientific work looks like this. You would define a problem. You design a controlled experiment. You test the theory or particular view with this experiment. And you answer the question, does this work? If it doesn't work, you try to control the factor in different ways and try to identify whether there are missing factor you're not looking at. If it does work this way, then hopefully you've advanced the theory one step forward. So scientific work is very clean-cut, very well-controlled in laboratory setting. So this is all great for 400 years. Have pushed us really far. Here we have airplanes. We're going to the space and all of that. So can you think of an example of scientific thinking in your work? And did it help you solve the problem? Or did it not?
You're already working in science. You believe in that on the premise that it should work.
Sure, it works, right? This works in science. That's why we have all these advancements in science. Yeah, absolutely. Absolutely. Yes?
I think we have a lot of examples. I'm a pediatric neurologist.
There's a mic. Perhaps everyone can hear you better. Thank you.
And a physician, and there have lots of recommendations health-wise that have been proven scientifically, but until they understood about genetics, they didn't appreciate the complexity of what they were even looking at. And so I think if we focus down minutely enough, we maybe be able to reveal mechanisms, but in real life, things are a lot more complicated than we'd like to think.
Can you give us an example that we that are not biologists can understand?
Let's see, a lot of men in the audience. Somebody recognized that the PSA, a chemistry in the body, goes up and was associated with men that were thought to have prostate cancer. So they recommended to follow the PSA, and therefore anybody that had an elevated PSA to recommend them for some kind of treatment, only to find out many years later that those two are not tightly linked. They're not cause and effect. They're associated.
Correlation.
And so we found out that, and I'm actually very interested in this session because I tried to teach physician faculty to teach systems to fledgling, and their scientific background is a real handicap.
Well,
So I'm hoping engineers have some.
we can work together. Thank you. That's a very interesting example of correlation being mistaken as causality. And I think that happens a lot, especially now that we have the big data discussion. And you may see actually a lot of correlation in the data, but to prove causality, that's always the challenge for statisticians. That's great. Thank you. Any other example anyone want to share?
True. In case coming from an industry where we actually make drugs, the complexity is even more greater. But now that we know about the entire thing about the human genome, which 10 years back the first time the graph was published, and we thought we would know everything about human beings, only to realize 12 years or 14 years later, the complexity encoded in the string is 3 billion
That's very interesting. So I'm not a biologist, I'm an engineer by education, but in this whole domain of talking about emergence, biology plays a major role. People actually saw emergent behavior in biology a lot earlier than they see in engineered systems. So I'd love to hear your thoughts on this after we cover this material. All right, so for the time being, I'm going to move on to the next slide. So here we're talking about system design and management. Do we see reductionism in the way we approach designing systems? Yes, we do. We see it a lot everywhere. So here's an example. System engineering, the most common process out there in industry is the system engineering V. We go down the left hand of V from defining customer stakeholder needs to designing high-level requirements, more detailed specification, detailed design. Then we go up to integrate and test and verify, put it in the field. So this V of decomposing our system and the requirements from a higher level down to the lower level of the system is a reductionism approach. We want to cut it into smaller pieces so we can hand it off to our engineers and they can each work on parts of it. And does it always come back up the way we want it? That's the question, right? All right. So when we look at systems, this is a big thing. When you analyze or study system, we always talk about system scope and the resolution we're looking at. And this ties into the example that Genevieve had given earlier about the engine, the tractor, the software, the context that is working in. You can look at a system from different levels of resolution. You define a scope, and you say, oh, there are these major chunks. But each chunk, you can look deeper into it. There are smaller things, more elements in it, and each one of these can potentially be broken down. So system is always hierarchical. And you need to define the boundary and its resolution when you study it. All right, so here are some examples of complex systems. I talked about car. So here's a truck. A truck can be broken down into the body, the powertrain, the chassis. This is very graphical. And in a diagram way, this is a typical way a vehicle gets broken down. So this is a physical decomposition. We take a complex system. We say, here are the main parts. These main parts can be further broken down into these. So bill of material maybe represent this. A lot of times, the way companies organize represent the physical decomposition as well. We can break down the system by its function. Usually, people tend to say functional decomposition is more solution neutral. So you would break down the system by its attribute. And this is used a lot, actually, in marketing research in the automotive industry. And in marketing research, you would describe a product by its attribute. You would not say, well, I will have a curved handle like this. You would say, provide an ergonomic grip. And is that an important attribute to the customer? Are they willing to pay more money or less for this feature? And you say another feature is pleasing color, something like that. So you would describe your product as by its features, and then you do conjoint analysis and all the other sorts of marketing research techniques to get a willingness to pay, so on and so forth. That dictates your product direction. So you can functionally decompose your system as well. There are other ways you decompose your organization, and a lot of times this may or may not match your functional decomposition, may or may not match your physical decomposition. And that mismatch sometimes can create interface issues because research has shown people in different teams located in different buildings and locations tend not to communicate as well as people within the same team or located in the same place physically. So that lack of communication can create a lot of interface issues in the system. So we do decomposition all the time, and this is a divide and conquer approach. It is a reductionist approach. What are some of the benefits of doing this? It's probably obvious. Anyone want to?
Each engineer has some amount of work you can done and something that doesn't work.
You can, yep, they're trying to give you a mic.
Oh, okay. So I said each engineer this way has something he can focus on and a certain amount of work he can get done
Right.
in a finite work week. Whereas if you tell somebody, okay, go down a truck.
Yeah, Yeah.
Especially if you wanted to make a completely new truck instead of just slightly modify the old truck,
Yeah.
right? You don't know, without that, you don't know where to go.
We all need this. We all need this. This is why we have specialization. We need the teams to work on the project because there isn't complex system isn't something one individual can just do it by him or herself, no matter how smart, capable you are. Therefore, divide and conquer is very smart. It's a strategy. We can't avoid it. But what are some of the challenges? Is that enough? Is that good enough? Just divide your work to your engineers or team? And does that guarantee a good outcome? There's a hand in the back.
Hi, my name is Jonathan Quata. I work for Ford Motor Company. And I guess we follow the same type of decomposition or trying to divide and conquer, but one of the main challenges we face is about communication between the new entities you are creating. How to ensure that the communication and the interaction between the new reduced entities is working well to actually have an efficient system function or emergence. That's one of the challenges I see.
Thank you. So he's touched upon this interaction issue that we had discussed a little bit here. It's good to divide, and everybody has a defined piece of work, but it also needs somebody to oversee how the interactions happen. If you don't oversee that and leave it alone and just assume it'll happen no matter what, it might not always happen the way you want it to be. Yes?
There is a standard.
Sorry, I'm going to throw your mic just so that everybody can hear you.
I was going to say there's a standard way of dealing with that, right? Which is you do interface control documents, whether they're logical ones or physical ones or organizational ones, that try to make sure that the various parts are working together properly. Right.
That's a good
know,
way. That's a good way.
Right.
In our class, we teach design structure matrix method, interface management, change management. So there are lectures touch upon all of these interface issues. That's very good. Have you seen, what are the challenges you've seen with interface control documents? I am sorry. Usually in our classroom, everybody has a button. They can speak to them. Like, this is a special.
So first of all, they're very hard to get right? Because it's very easy to have people on either side, whoever's actually drawing it up, make an assumption without stating it. So it's hard to get right. It's hard to test. And also, they're very complex. So sometimes you sit there and people are busy designing parts while the interface document is being done. And by the time you realize they had it wrong, or they left out a definition. I remember one early in my career where it was a radio communication thing, and somebody forgot to figure out what time zero is, zero reference for time was. And two different people implementing it on different things just made a different choice.
Yeah. We've seen a lot of these
You
examples.
had to fix it.
Yeah, absolutely. So there are ways to address them. And I'll get to all of you very soon. Let me just make this comment. A lot of my research, actually, when I was a master's degree student and a PhD thesis research, was to try to capture interactions and try to predict interaction. And one of the interesting finding, not my main thesis, but it was a side finding, was the fact that a lot of this interaction is not well documented. And I went to several companies, different projects. About 70 to 80% of interaction, the true knowledge resides in the human expert. It's not well written down. And it's hard to write down because things change. Things really change. And the effort to document and update the document is almost behind. It's behind. You're focused on delivering the product. So this interaction is challenging, and we were even trying to come up with expert systems that try to automate these interactions. And really, they only work on very small, stale system that never changes anymore. The one that integrate with the rest of the vehicle a lot, that doesn't work because you just can't capture that interaction so accurately. All right, let me take a hand here.
Well, it seems to me that in addressing that problem in the design, there needs to be feedback loops built in because the internal and external environment can actually change.
Can we move to the last slide, actually? I think I'm done.
practiced.
That's great. I'm glad. You might find some of the slides later will
And that's the
resonate
problem
very
with
well.
leaders. They like a nice, clean design, but they forget that their design is probably outmoded as quickly as if it's static. It has to
Absolutely.
be dynamic.
Thank you. And you had a comment as well, no? And there was, yeah.
Well, I guess just to build on the integration piece, it's, you're talking about letting everybody divide and conquer and do their part and then bring them back together for integration. But also with that, it allows, that has to happen multiple times. And besides the integration piece, it's also keeping the priorities straight for the overall project. It also allows people to have a fresh look at the other pieces because they're so engrossed in what they're doing. But having the group take a fresh look is often helpful for looking at solution development. And then also to take a look at the timeline because as we all know, things get off schedule.
Absolutely.
And if we can catch these things early, then maybe we can prevent, that second and third order effect down the road.
Great points. And I sound like I'm advertising for SDM program, but I am one of the core course instructors, so I'm somewhat familiar with all the materials we're teaching. And a lot of these issues, we talk about them in the class. There are methods, there are tools that can help you do better, and one of those you will see later, I believe, in Brian's lecture. And this is what the program is about, is to try to address all of these challenges you have brought up. Was there a hand I missed? I'll take one more so we can move on, and perhaps we'll make comments later.
Well, it's interesting, the three structures you showed for organization. One was kind of component structure, another was a functional structure, and the other one was the hierarchical structure. And actually, all three of those can come into play at the same time. And
They
you get
always
this
do.
three-dimensional structure then that's really difficult to work with. And often the command media produced, when you start looking at those and trying to tie them all together, the larger the organization, the looser the command media has to be. And sometimes it doesn't get as detailed as the system requires for success.
Right, and those are challenges. You do have multiple views of a system. And you, as the leader in this process, we needed to think more holistically. We needed to look at those aspects. So just delivering, again, the message I'm hoping to deliver today is just having good components are not good enough for complex systems. And there are ways, and the framework I'll present is, to me, a mega kind of view, a higher level view, and many methods and tools we teach tie into this view of thinking about system as a feedback control system, actually. So I'm going to move on because of time. Thank you for all the great feedback and comments. So, we touched upon this, and that not only our own experiences, history have shown some of the greatest people worked on some of the most complex systems that human at that time had addressed, come up with the same comment. So Eugene Kranz said in The Failure is Not an Option, says, not a single mission went according to plan. And sometimes replanning begin immediately after launch, right? With one exception, no failure that they practiced actually ever happened. So that's complex system. Dynamic, hard to predict. Things can go wrong, a lot of interactions. Charles Mueller says, in spite of the massive scale of the Apollo program, in terms of both the resource applied and the technology used, the major issues were ultimately resolved by a small number of people making very difficult decisions in the presence of great uncertainties and unprecedented technical complexity. So again, this is complex system is challenging for human beings because we all have limitation in our cognitive capability. Complexity is not something in the world. The world doesn't care. We care when it's relevant to us. And we have a hard time dealing with high complexity. So that's what's challenging to us. Napoleon says, I want the lucky generals. What does that mean? I want the lucky generals. Luck plays a lot into the dynamic process of the war. Eisenhower said the benefit of plan is planning, not the plan. So I just came out of my resource planning for 2015 fiscal year. And I thought, wow, why did I spend a whole hour guessing what percentage of work we're going to put in? Because never, ever in any previous years that had been the right guess. So we have to plan and plan, then we need the breaks. That's what General Patton says. You work really hard, and then you have to be lucky. Dr. Draper said that. So all of these great leaders in technology, in warfare, complex human systems, make the same comment. They're good planners. They know what they're doing. And yet, complex systems give you uncertainties, dynamics that are really hard to anticipate. So the problems with scientific thinking. There are two problems with scientific thinking, two major ones, is that the reductionist thinking, several, there are two I want to emphasize today, but reductionist thinking, as we have explored, divide and conquer the pieces. It can't solve the problem of interaction and emergent properties of the system. So we talked about that. A lot of the illities we talk about in this program, quality, safety, flexibility, maintainability, these are system attributes that you can't pinpoint on one component. They are the collective behavior of the components when they're interacting with one another. And the physics and the chemistry are restricted science, where well-designed experiments are possible. You can control factors. You can have repeated experiments. Unrestricted sciences such as biology, geology, where there are many, many factors, it's harder to identify them and harder to even control them. Well-controlled experiments may not always be possible. So even more important and relevant to what we're doing in system design and management is when the human enters the space. When the human enters the playground, things really change. Human is a major component in sociotechnical systems that we're dealing with. And they don't behave like computers or mechanical hardware. Human decisions may not be rational, repeatable, testable. They're highly contextual. And the prediction you make will change the human behavior. So it's very hard to verify whether you predicted the right thing. Because once you say, today if you drive on Route 128, there's going to cause a lot of traffic jam. Everybody won't get on that highway, then you won't see the traffic jam. So did you predict it or did you not predict it? A lot of times in our work, that kind of experiments are very difficult to set up to verify whether you had predicted right or wrong. So on this note, I actually inserted an interesting thing happened recently, and let me see. Do you recognize what this is? Ferguson, Missouri. I just pulled a picture from the web. What happened there, right? This police officer, Darren Wilson, and shot person Michael Brown. And there has been a big riot and a lot of social unrest and a lot of discussion about racial inequality, justice, so on and so forth. So what happened really there got me really interested. I don't want to get into the discussion about social injustice. What is relevant, the piece that's relevant to our work is I think this shows a great example of how humans are different from computers. So I want to focus on how do police officers decide when they should use deadly force or not. And I found a lot of interesting literature, and I'll show you which ones they are, and how police officers make that decision. Now, are they given rules and guidelines? Absolutely. So there are three, at least, laws they have to follow. There's the federal law, where they can't just pull out a gun at anyone. It has to be they have to use a deadly force only to defend against the attacks that would kill or seriously injure them or others. You can't just shoot at anybody that's running around. That's the federal law. And the state laws on the use of deadly force can only be more restrictive, not more relaxed than federal law. So every state have their specific laws, further restrict what the officer can do in terms of using deadly force. And then each individual police agencies in the town, in the city, in the area, they have their additional shooting policies that are only even more restrictive. And then when the officers come through the academy and through their training, what they each individually develop are further shooting policies that they guide their own actions. So as you can see, this is kind of like requirements, right? You got the high level, more restrictive, and the local requirements. With all of that specified there, the police's action in every case is different. The context is highly dynamic, very, very short time reaction, very, very dependent on what's really happening. And there has been great documentation of how police officers make that decision or not make the decision not to shoot. So there are a lot of cases, and I found these reading fascinating, Into the Kill Zone and the Maxwell Gladwell's Blink in its chapter, I think it's the 7 seconds or 6 seconds in the Bronx example. So there are lots of examples showing in cases where a police officer, all these cases, police officers legally are allowed to shoot. But depending on the circumstance, they choose not to shoot sometimes. Sometimes they choose to shoot. So there are a lot of stories about shooting to protect a fellow officer. And I read one of them, I remember, was actually this Professor Klinger. He used to be a police officer. And he opened the book by telling the story when he fired his gun. And it was a case when he and his partner were on a call to address a robbery. And this person had a duffel bag. When they told all the bystanders to go away because there's an armed robbery happening. And this person didn't go away, stayed on the sidewalk with a duffel bag. And his partner walked up to this person and wanted to tell this person to go away. The person suddenly pulled out a knife, started stabbing the police officer. So the second officer, who's the author of this book, started running towards the scene and wanted to protect his fellow officer. And it was a very vivid, graphical scene. And eventually what he ended up having to do was he saw the person use the knife, stab his partner multiple times on the body, on the torso, and he just shot the guy, and then the person died. And he himself afterwards was really in big shock because he reflected upon it. It was a person he's never seen before, couldn't even tell what the face looked like. But in that couple of seconds, he took the life away. And it was completely legal because that person was attacking his officer, the other officer, his partner, and it was a self-defense, and it was a criminal act that he stopped. So they do that. Now there was another story in the same book where the police officer was on a call for a suicidal person in a parking lot. This person was, again, using a knife, but on himself, and it says, I'm going to kill myself, going to kill myself. So other officers were there and shouting at him, please stop, stop. And this officer said to him, hey, you need to stop, because if you don't stop, I'm going to shoot you. And that guy says, okay, well, shoot me. I want to be shot. And the officer was aiming at the person, and the guy just started wielding the knife at the officer, started charging towards the officer. And in that instance, the officer's life was in danger because the person is using a weapon against him. And he could have very well shot the guy as self-defense and be done with, and totally legal, no problem. But in that moment, what he decided to do was to kind of back off and see if he could stop the situation. The person got really close, but every time the person got close, he stops and started screaming and then ran back to where he was. So that repeated 2-3 times. The officers told him that if you stab yourself, it really hurts. It's not a good way to die. Please stop. The person kept on going back and forth. So at one point, the person finally said, okay, yeah, I don't believe it. And he stabbed himself in the stomach. And that really hurt. And he stopped. And the officers ran up and kicked off the knife and arrested the person. So this officer was describing this whole experience and saying afterwards he felt really good about not having to use his gun and kill this person, and was able to rescue his life and send him to the hospital. So again, legally, He could have totally shot the guy and protected himself, but he didn't do it, right? And then the third story I remember a lot is the 7 Seconds in Bronx in the Blink book, where they talked about a mistaken shooting, where 3 officers were on patrol in this really bad neighborhood, bad street in the Bronx, a lot of robbery and things happen. And they saw this person standing on the porch in the late night and looking around. So they said, okay, this looks like a type of robbery where somebody pretends they're visiting and they try to get into the door and all that. And it so happened this person was an immigrant from another country. His English was poor. He doesn't have much money, so he's living with a friend. He just came out at night and started enjoying the evening. And he was standing there wondering and looking. So the police officers stopped and started yelling at him. And he doesn't know what the officers were talking about, so he was confused. And the officers got out of the car, and they had a weapon in their hand. And this person was just robbed a couple of days ago with an armed robbery. So he thought it was people coming to rob him again. And he started reaching into his pocket. And that's a bad thing, because the officers thought you're reaching to get a gun or weapon. And they got really nervous. They told him not to move, don't do it. But the guy didn't understand. He kept on doing it. So the officer got close enough, and the guy wouldn't stop, and they thought he started pulling things out. And they shot the person and killed him. But when they got up there, they pulled his hand out. The guy was trying to pull his wallet out. I think he was trying, the suspicion is he's trying to pull the wallet out, say, take my money, I'm okay. So he died, and the 3 officers were actually, I think, charged with murder and had to serve sentence on that particular one. So all these stories, they're fascinating. What I think what they're telling us is that, humans are not machines. Going back to this slide, human being making decisions really based on the context. So when you're designing a complex system that involves human, either human as the operator or as the decision maker or as someone that carries out processes, it's a false assumption that human is going to behave every time as they're told to. Even in the police case where they are told with a lot of restriction what to do, what not to do. Every context presented things differently. Every officer made different decisions. So if you're running a factory, think about your operators in the factory. Do they always do what you tell them to do? And the expectation that if you give them written procedure that they will follow, that's a false hope. And also on the flip side, do you really think a human always cause trouble? The officer that didn't shoot and saved the life of this suicidal person, he was actually doing a good thing by not shooting because he saved this person's life. And we've seen heroes that saved the situation last minute because they were flexible, they were able to react in a way that saved the situation. So human flexibility actually is a good thing. And to expect that having human in your system and carrying an experiment out, and every time you get the same result as a scientific experiment, that's a false assumption. Humans don't behave like mechanical components. So that's one major challenge in this reductionist thinking, that you think you can't have human behave the way as computers and as parts. They just don't. So the last point is management science. Is a science where we try to put some structure in this thinking, try to model and predict the behavior. And that's all good, but the operations research as the main example, real world phenomena are not always well defined, and that's a challenge in that field. Decisions must be based on multiple criteria, and humans don't always make rational decisions. That's also well documented in psychology literature, in behavioral economy. Why do we all end up buying lotteries when it's, $600 million, jackpot, and we don't buy it when it's $10,000 jackpot? Your chance is probably just as good either way, but somehow we thought we had a better chance when the jackpot is $600 million. That's because the loss aversion. right? Because your reward is higher. So you feel like you have more chance. You go there, you spend your $30, $20.
Your expectation value is the product of the chance and the payoff.
That's right, that's right. So the value, the chance is the same, but somehow, we always behave like that. And there are many cases, once you see a flood nearby, everybody start buying flood insurance. A couple of years later, nothing happens, everybody starts dropping the flood insurance. That's well recorded, earthquake insurance, so on and so forth. So there's this book, Thinking Fast and Slow by Kahneman, Nobel Prize winner. It's a wonderful read if you ever get a chance on how human may make decisions in an irrational way. But that can be studied too, modeled and understood to a certain degree, and that's what behavioral economy is trying to do.
Well, but even parts, we model statistically quality, right? For instance, metal fatigue, we don't model it as you bend this 600,242 times and right, you get some statistical distribution.
Sure.
And you can do that with people to some extent.
You can. And you can, and they're relatively harder than modeling metal fatigue. Yeah, this is not to say we can't understand human behavior, but it's additional layer of challenge. So with all of that, so those are the additional challenges when you work on complex socio-technical systems. Therefore, it brings the need for system thinking. And when we think about system thinking versus scientific thinking, maybe this is a good break point to introduce this thinking about why are we talking about system thinking, scientific thinking. This is really about building a model in your mind of how to look at the process or the world that you're studying, right? It kind of has the analogy to, say, a long time ago, people believed in Earth was the center of the universe. So when you have that mental model, Earth is the center of the universe, you can explain some of the phenomena, such as the moon goes around us, certain stars seem to move around us, but some others don't. They have very strange trajectory, and they have strange patterns. And a lot of the stars, the phases of planets and stars, they become really almost impossible to explain. So using the geocentric model, trying to explain things you can observe, it becomes more and more and more challenging. That's when people say, hey, maybe it isn't absolutely correct. Therefore, the heliocentric model comes along. It was able to explain a lot more the phenomena. So the mental model of going from geocentric to heliocentric is sort of a paradigm shift. So of course we know the sun isn't the center of the universe either. It's just a star in the Milky Way galaxy, and we're just one galaxy in the whole universe. But still, this change in the model helps you to explain more and more, understand more and more phenomena. And that's what I'm hoping that scientific thinking would do for us as well. So scientific thinking, systems thinking would do it for us. The main idea is really is not a complete different thing. So the ideas can be found in biology and in communications and the controls engineering. And it's really a focus on the irreducible whole. There are two sets of concepts associated with system thinking. One is emergence and hierarchy. One is communications and the control. And this thinking can be applied to many, many disciplines. So let me expand on emergence and hierarchy first. Emergence and hierarchy, I'm not sure why the graphic did not come up. Okay. What you're going to see is just the white couch. Imagine IKEA catalogs. Or just look at the chairs. If I ask you, would a white couch be a nice thing to have? How would you answer that question? All right, that's very good. You're asking how I live, right? It really depends on where you're going to use it. So it might look great on display, but it might look really bad in your life. How about this one? Is this a nice coffee table? So students in our class learns the good MIT answer. Yes. Thank you. It depends. It depends, again, where you put it. Now, the way they put it together make them look quite attractive, at least from my point of view. You might not agree, but I think this is a nice-looking living room. So it really depends on where you put it, how you organize everything. I'm losing another graphic. So this one is just showing an ugly combination of a perfectly normal set of couch and coffee table as well. So if we just take a decompositional view of a room, imagine you're moving to a dorm, you're going to get some couch and a coffee table and some decoration. This is decomposition, right? All right, send your buddies out. You get a couch for me. You go get a table for me. You go get some vases for me. Do you think it'll come back and give you a nice-looking room? The chance of that is relatively small, right? Without any coordination. But that's what reductionism does for us. You decompose, you assign the tasks off. So what's missing in there to get a good-looking interior is some kind of coordination. Why do you need that coordination? Because there's this emergent property of the look of the room that comes from the interaction of these pieces and the setting of the room. It really depends on what kind of room you're in. So emergence and hierarchy is a concept about the world's complexity is hierarchical. And there are different languages and the different properties at higher level of the system versus at the lower level of the system. And at the lower level of the system, the higher level properties are not obviously visible. That's emergent properties. So I like to use a car example because a lot of my industry experience are in cars, and hopefully you can relate to what you've worked on. What are some of the properties people care about at this level? This is the whole car. Aesthetics, attractiveness, how does it fit into my work? What would my friends think of me if I drive this car, right? This is a fuel cell vehicle inside. What do you think engineers think about when they're working on a fuel cell powertrain? Accessibility of the hydrogen tanks, recharge the tank. Okay, all right. What else? The weight of the system. Maybe the performance. How long would this go per refuel? How far can it go? How fast can I accelerate, right? How long would this last? Would the tank be safe? How durable is it? So on and so forth. Can you see this at this level? Not obvious, not obvious. How about people working on an internal combustion engine? Genevieve, what are you thinking about when you're working on your engine?
What am I? All right, that was a real question. Yeah, I mean, there's a lot of it. It really it depends. How's that? On
Super.
what you're. I mean, am I thinking about a particular subsystem again within this, or am I thinking about delivering power or torque, or how much fuel I'm burning, or what does my maintenance schedule look like on fluids? I mean, there's a lot of different ways that you could.
Yeah, so you're worried about the engine performance, maintenance, reliability, quality, so on and so forth. And it is not obvious. Apparently, some of the graphs just disappear mysterious. So it's not obvious at this level to see the attractiveness of the car, of the vehicle. What about the people designing the combustion process, the thermal process, the injection timing, the design of the piston, the delivery of the torque, the camshaft, the crankshaft? The folks designing that is even more inside of the engine. They may not even see the whole thing about the engine. So all of this is trying to say that, try to give you an example that a complex system, I mean, this is not the most complex system in the world either, but fairly complex as the automobile. You know, as the decomposition goes down at different layers of the decomposition, engineers are focused on different properties, behavior of the system, and they're not necessarily, obviously, seeing how their work fit into the higher level system. It's not obvious. So there are properties at the higher level of the system that are hard to observe at the lower level. I see a hand with some comments.
Yeah, just Chris Huffman here from Cummins. I would argue that some of the properties you're talking about emergence at higher levels of the system are equally valid at the lower levels of the system. Different perspectives entirely. You talk to a piston designer or somebody on the turbocharger or even the power cylinder that you have shown on the bottom left there. There's going to be some level of aesthetics and other properties that are equally, same requirements perhaps, but totally different targets in that particular perspective of that system of interest.
Sure. They might like a beautiful looking component or part, absolutely. So, but it'll be at a different kind of, with a different meaning versus the vehicle being attractive and sells well in the market. So, good comment. And the other point I wanted to make is it completely irrelevant? They are relevant. So how attractive this vehicle is as a whole can relate to how well the engine performs, the kind of noise it makes, the kind of packaging it results in. If you have a really tall engine, you can't have a low hood. Would that make your car look really bulky and then not sell in the market you want to sell? So they are related, but that relationship is not obvious. And that's the challenge when we design a complex system, is you really deliver the high-level attributes as a system as a whole. But you needed to be able to decompose that attributes to the lower level of the system so that when you divide the work to your engineers, they are doing the work that march in the same direction at delivering the high-level attribute. And that's always a challenge, this decomposition and flow of requirements up and down. So we talked a lot about what emergent properties are. And one important aspect is in order to achieve the emergent property at the high level of the system, what you need is a way to control the lower level components' behavior so that they would behave in such a way that delivers the property you need at the end. And if you don't impose that control and the constraint, you just let the component do whatever they want, and that's Murphy's law, or the second law of thermodynamics, which I'm not sure if everybody here still remember, but its entropy always increases in this world without control. So you need to impose control so that you get the desired outcome at the system level. And here are some examples in my work experience. This one's interesting, and I might skip the next one, where I was working in an automotive company. It's a US manufacturer. So imagine the kind of SUVs you see among US manufacturers. We get J.D. Power rating back. We're rated less roomy than our competitors, non-US competitors. So the advanced architecture team was given the task, figure out how to make this roomier so customer gives us 5 points instead of 3. All right, the engineer said, easy. Roomier, that means make it wider, taller, longer. Well, we're not famous for being small with our SUVs. So what's happening? And we took the SAE, Society of Automotive Engineers, has a set of standard dimensions across board to describe the vehicle. And you see in Elements.com and car sales, they'll give you these kind of head height, shoulder dimension, the knee clearance dimension, so on and so forth to describe the vehicle. We benchmarked our vehicle against our competitors. Where you see a red number means the competitor is smaller than us, but they were rated higher in roominess than us. Now, roominess in this case, it shows to us, is not a simple decomposition of dimensions. Larger dimension does not translate to human perception as being necessarily roomier and more desirable. The smaller vehicle with other factors, whatever they did, made people perceive it as roomier, and rated them higher. So that was a very, very educational experience for us. And all right, so with emergence, with wanting the need to control and constrain the behavior of the components, what comes is the need to impose control. And because you need a control, you need a communication, because control always needs to know what's the current state and then communicate the actions to change the state of the system. So that's the concept of control and the communication. If any of you are in the control systems engineering, this would be a very familiar concept to you. But even in pediatric area, sounds like a feedback is also biology is also a very familiar concept for us. So what does that mean is we wanted to be able to see whether we have a good feedback control system. And this is what a feedback control system is. You have a controller who has a model, whether in the computer or in your head, about what's going on. And the controller needs to have a way to sense what's happening now and compare that state with its own mental model and decide, is this good? Is this not good? If you are off, the controller needs, again, a way to change the system state, to bring the control of the process to the state you want. So this is a feedback control system. And this, in technical systems, this exists in all kinds of places. But in human systems, this can exist as well. So here's an example. What do you think when you're designing your living room? Who is the controller? Do you see a controller? Did you have?
The client.
The client.
Professionally, the client.
Or yourself, right? If you're the one that's going to live there. Or if you're the interior designer, your client. Maybe not your client, actually. It's you. You're the one making the decision for your client, right?
And I get paid accordingly.
Bonus for being a good system engineer. So this is the way it probably would look. You're either yourself or you're the interior designer. What are the sensors? What are the sensing information? The answer is right on the screen. I think class is getting long. All right, yeah. So your client's feedback. Or you go look, you go take a side view. You might be prototyping. Maybe you have some virtual mock-up, and you say, hey, does this look good? You know, with this fabric, this color, this wall paint, so on and so forth. And then your actuator might be the movers, the painters that's helping you doing all the work. And the control the process or the plant is the room. Eventually, hopefully, with good feedback control, you can get the desired output. One thing very important is also a good interior designer, what he or she really has is a good process model. They have a model about how to come up with a good room design. You know, a not so great, an untrained person like me, I don't have that model. So it will take me a lot of time, a lot of experiment to figure out how to do things in a way that perhaps the professional are trained and taught to do. How about this case where we were doing roominess study? Who would be the controller in here? The engineering designer, the design engineer, right? What kind of sensing mechanism could this engineer have?
There's probably models of average heights of people and body dimensions.
Okay.
I'd have to go by.
Okay, so that would be actually models, the mental model within the controller brain. What kind of sensor information could he get? Surveys. That's good, yeah. So what we did a lot was customers' clinics. We would bring in competitor vehicles, we mock them up, we have people come through and rate different things. Their survey sheets, the survey becomes a sensor, their answer sheets are our sensor inputs. And what we did was we tried to, okay, so I might have have a wrong. So what we did in this feedback control model is we, as a controller, as researchers, we're developing models that can translate customers' rating to certain parameters that we're adjusting in the car. So not only the dimensions, but other things, such as the seat positioning, the cushion thickness, the color of the interior, certain features, curvature, and the things on the roof, and so on and so forth. So we were trying to build regression models to see correlations between those factors and the people's score to our design, and hoping to build that model, and we can translate it into the future products. So that activity is very much a system design activity. What it fits in the feedback control system is the process model, again, within the controller. And then we have the engineering team sign up to help us carry out execute the design changes. So those were our actuators. And the management direction and all of that is sort of the enabler for the communication to happen. Otherwise, they don't really care for the research results. All right, so this is really a high-level view of system thinking. What I had to cover, we're kind of running short on time. So what I have covered are the properties of complex systems and the system thinking in two aspects, hierarchy and emergence, controls, and the communication. How this fits into the SDM program is the SDM program in our lectures, where we teach a lot of models, methods, approaches. Almost all of them can fit into this way of thinking. Some of the techniques are about how to collect better data, how to sense better. Some of it is the model about your system. So things like system dynamics we teach in this program, design structure matrix method. A lot of the methods we teach is about how do you model your system better to better understand and analyze certain aspects of the system so that you can issue as a controller, as a manager or the lead of the system design, you can issue the right directional command for your team to move in a way that your system design is more successful. And I like to throw this up and to say, perhaps the feedback control terminology sounds very engineering, but this thinking really applies to the entire social aspects of the system as well. This is a typical regulated industry. A lot of the industry in the US are regulated. And you can see here's really where a lot of the engineering focuses are, your technical system, your human operators. But really, the success of this system depends upon two major branches. This is how the operations side. If you have operations for your system, such as the air traffic control system, that's an operational system, the maintenance of the aircraft, other complex system. So how do you manage that operation? The decisions of the operation management, the company that owns the operations management, their culture, their decisions, whether they're getting enough information about what's really happening in the field, and are they correcting their course of action to ensure things operate on track. Whether any of these are happening in a timely fashion, that's very important. And then further up, where a lot of my work currently touches on is on the regulation side, whether the regulators have the correct understanding of what's happening in the industry. Are they correcting their mental model in order to better regulate the industry? All of that. Are the current regulation effective? Are they being assessed on a frequent basis? Those are all questions. So we're talking about, on this side, the system operations beyond the immediate little technical system you're using. And the design and the management side of the system in the same way, how are you making your design decisions? How is the management culture encouraging certain decisions or not? Do higher level managers have the sensing mechanism to really know what's going on down there and to be able to understand what corrective action should they be taking? So all of those questions can be modeled and identified in this hierarchical fashion. So I just want to say in the last 2 years, the SDM Best Thesis Awards have gone to students who has put this thinking into their work. So this year's Best Thesis Award, our recipient is in the audience, Stephanie Gorgeous from Commons Engine. And she was able to apply this thinking to their quality management process, looking at both the technical side and the management side, how to improve the cadence of meetings and better prevent problems in the company. The previous year was the Coast Guard student, looked at how Coast Guard had accidents during their training and how could they in the future prevent it, not only from a mechanical component failure point of view, but further up the stream, looking at their process and their acquisition, the entire acquisition process and the training, and where are some of the lacking or holes are and how to improve those. So both theses have won Best Thesis Awards in the last 2 years, and therefore, in many ways, demonstrate the power of systems thinking. All right, so I only got 1 minute left. Perhaps instead of discussing the system you're working on, maybe if you have questions for me in the end, then yes, go ahead.
Yes, thank you. This was very interesting. When you teach the class to the students, do you assume vertical integration, or do you actually incorporate the concept of vertical integration into system thinking?
Vertical integration, expand that a little more.
Well, in terms of alignment of resources within an organization, the assumption is that if you're truly vertically aligned, you have better than half a chance of achieving your goal. So the idea is that you want to have all those resources vertically aligned as opposed to being scattered across the landscape of the organization.
Okay, thank you. I make no assumption about your organization, the way it's organized and apply resource. So this kind of approach, what it does is to just draw out what your organization looks like now and ask the question, do I have all the feedback channels that I needed to have? If resource is a reason that you don't have all the information you need to make the right decision, well, that helps you to look at that problem and to think about whether better aligning our resource is one of the solutions. So we make no assumption about how you do it, but rather ask the question, you know, what's lacking and where should you think about improvements? You're welcome. All right. Do we have one more? Yeah. Thank you.
Just sort of question, but just a comment. If I may. So you did mention about the decomposition, and you had wonderful pictures of an automobile industry example. And then we come to the picture of a human being entering into this and how a human being controls. If I may, what would be the next one is if you look at the human being himself or herself is the greatest example of systems integration. And if you actually try to parse it down along the details, either vertical integration or horizontal integration, whatever you mean, you will actually begin to see all those examples you have cited of feedback loops, regulations, controls, actuators, except that you may have to give a different name. But almost every single such an event is actually happening and occurring. And as we speak, a billion reactions are occurring in your system, and they're all doing the right one, with an addendum that there are garbage disposal systems also at work for all the mistakes and errors that are being committed while the systems are working.
Absolutely. Absolutely. The idea applies. In the lower, for human, each individuals, we as decision makers, the organization we're working in, the team we're working in. So it's, to me, in my research experience, this framework of thinking is quite powerful. It goes up and down. It can go very detailed. It can go very high level, all the way up to the Congress and the way we regulate many industry in this country. I agree. So it's not this discipline specific, and that's why I feel this is a powerful way of looking at complex systems, and that's what we're trying to teach in this program, not just how to design an airplane, how to design a car, but a set of tools and the methods that are more universal and applicable in many domains. All right, I think my time's up. Thank you for your attention and the wonderful discussions. Thank you.
Thank you very much. We very much appreciate you coming and talking to us. We're going to take 1 minute to flip over the computer.